P-type semiconductor. So how to produce P-type semiconductor? A trivalent impurity atoms are added to intrinsic semiconductor. What are trivalent impurity atoms like gallium, indium, aluminium, all these are. So trivalent impurity atoms. What they are? Aluminium, gallium, indium. So all this will come as the trivalent impurity atoms. So here, let me write, this is Al. Let me. So again, it's a trivalent. So addition of one impurity atom. So it's like a trivalent, no? So there are three outermost valence electrons are there. So that will be shared by this trivalent impurity atom with adjacent silicon atom, and what it will do, it form a covalent bond. The fourth bond, you can see this one, this is incomplete, no? And the vacancy created by valence electron in valence band will become hole. So addition of one impurity trivalent impurity atom will create one hole. This is a donor, no? This is an acceptor ion. It is in need of one electron. So therefore acceptor. Pentavalent impurity atom. It donated one atom, it donated one electron to the semiconductor structure material. So therefore it was a donor ion. This will call as acceptor ion. So addition of one impurity atom will generate one hole. That will be, this hole is generated. So how the energy band structure? Again, same thing, 10 to power of 6 atoms, 1, the same idea it will be. Valence band, conduction band. So where the Fermi level acceptor level or call Fermi level. Don't bother much about anything, just only info data. Where Fermi level for p-type center, just above the valence band. Here, these were the holes. These holes are due to what? Thermal agitation. And these electrons are produced due to thermal agitation. Then, for addition of one impurity atom, that hole will come and settle here. Those also, they'll be very loosely bound. This one. So this is around in the books, they're telling 0.05 electron volt. If you give small energy, no, that will become free and it will be available for conduction. Where do it will come? It will come to valence band. So if you, what happen for electron, you have to supply energy. For a hole, what happen? It has to climb down. Always think about electron. You may get confused here. If the hole moves from higher to lower energy level, it will be available in the valence band. If the electron moves from low to higher level, it will be available for conduction band. So these are the holes available for this one. So what we did, again, just by adding impurity atom, for the addition of one atom, we'll get the one hole. Like that, if I just add few grams, no, millions of holes will be available for conduction. So I increase now the conductivity of this semiconductor. I'll call this as a p-type. N means negative, not like semiconductor is negative, just they brought the name n-type, and this called like a p-type semiconductor. So shall I say that these are like a acceptor ion? It is in need of one electron to complete the bond. This particular. So how we show that p-type semiconductor? So in the there's a square box. This energy band diagram. Then this this box is what very important, because this is what I'm going to carry on. The total almost around, I think, the whole week, it just revolves around this diagram. So what is acceptor ion? Trivalent impurity atom. Theory very difficult, numericals are very easy. Addition of one impurity atom will give one hole. Clear this. And along with that, there'll be free electrons. Why they are? They are due to thermal agitation. Now, shall we put positive sign or negative sign for this? Negative sign. So what is the net charge of this p-type semiconductor? Will be 0. So who are majority carriers? Holes are majority carriers. What about electrons? Minority carrier. When I say electron, no, it is that free electron only. We are not bothered about valence electrons in valence band. When I say electron, it's a free electron only. So this happens, and again here the same formula. And what is NH is equal to Na. How many like a trivalent impurity atoms and those many corresponding O's will be generated. I know what is that. There are some O's which are due to thermal excitation, but this number will be very small compared to what we had. The O's generated due to the doping, what that generated will be very much greater than the O's generated due to thermal agitation. So therefore, this is an approximate formula. So how many acceptor ions, how many trivalent impurity atoms had, those many O's will be generated. Substitute that, and this will be given for a semiconductor material. You'll get the minority carriers. How many minority carriers are present? Just as a formula based, no? Just they give values, you have to substitute, you'll get the answer. It's very important. 2 times they've asked in mains again. This is about the p-types. What is the net charge of the p-type center? Will be 0. It's a neutral. Okay, now look at this. What is the state of this trivalent impurity atom? Can it move? Can it move similar to free electron? No. So shall I say it's a immobile? What is a mobile? The hole is mobile. As hole can propagate. Yesterday I discussed that one. Similarly, come for N type. So there's a trivalent impurity atom, no? Sorry, donor ion. Now, is it mobile? No, it's also immobile. It cannot move. Why it cannot move? The adjacent silicon atoms will not permit, no? So they're fixed in semiconductor crystal structure here. Only they can, due to rise in temperature, they can have thermal agitation. Means they can vibrate above their mean position. It can vibrate. It can vibrate, that's all. But it cannot. So therefore, shall I call immobile ion? It is immobile donor ion, immobile acceptor ion. Later, I'll be using these terms. You should have this basic picture here. The Fermi level for p-type semiconductor will lie just above the valence band. The Fermi level for the n-type will just lie below the conduction band. Okay, there's a overall the way what happened p-type n-type will put it, and both are electrically neutral. Both n-type and p-type is neutral. You write it nearby. Net charge of it is 0. This is electrically neutral. Okay, this is about the construction, like how to construct the p-type n-type. Okay, let me bring these two and I'll join them. So usually what is a silicon? Solid, no? What about the impurity atom? They're in solid. But how do I dope? They are not in solid state. They'll be in molten state. And that what when I should take the pure silicon, not like something that one. Pure silicon it should be. How much of purity? 99.99%. This much for pure silicon. I should add the impurity atoms. And both the impurity atoms which I'm going to add and silicon will be in the molten state. Now like this I'll construct p-type n-type. Now if I join them both physically, anything will I get it? I'll join them means